On the Q1 district assessment for pre-calculus, it's going to cover Unit 1, topics 2 to 3. It's 10% of your quarter grade, and you will be provided with a scientific calculator in the Performance Matters website where we will take the test. So you should click this link on the PDF and open the Desmos scientific calculator so that you can get proficient with using this type of calculator while doing the work in this review packet. Every district assessment, you will get a MCPS formula sheet. For Q1, none of these formulas apply. They will actually help us third and fourth quarter, but nothing on either page of this formula sheet applies to Q1. So let's get started with problem 1. So turn past the formula sheet, and we've got describe the following as even, odd, or neither. And this is symmetry. Even symmetry is y-axis. Odd symmetry is origin, or you could rotate that graph 180 degrees, it would look the same. And neither is neither. Proving this algebraically is we're going to input negative x. And let's simplify. So negative x squared is negative x times negative x, which is positive x squared. Negative 3 times negative x is positive 3x plus 6. So now when I compare to my equation, x squared, that's the same. Negative 3x, positive 3x, those are opposite. And 6 to 6, that's the same. And so when we mix and match, that is a neither situation. For B, now, because we have that scientific calculator, I'm going to use numbers to prove the symmetry instead of an x. So let's input negative 2 and let's input positive 2. And when I input those numbers, I can compare the final results to see if they're the same or opposite. So if they're the same y value, that would be this even symmetry that for positive 2 and negative 2, I get the same result. If I get one positive value and one negative value, same, like if this is 7 and negative 7, that would be odd symmetry. If I get two numbers that aren't related at all, then it's going to be neither. So let's pull that scientific calculator, and I'm going to type exactly as I see it. So negative parenthesis, negative 2 parenthesis. This is the squared plus 4 times negative 2 minus 1. Oh, sorry, that's negative 13. Let's see what positive 2 gets us. Negative positive 2 squared plus 4 times 2 minus 1. 3. These are not the same number. They're not the same number but opposite signs. So this is neither symmetry as well. So you pick your favorite method. I'll do the numbers again for C. If you prefer the X's, you can do the X's. So I'm replacing every X. And I'm just choosing negative 2 and positive 2 because, I don't know, I like 2. You could pick 3, you could pick 4, whatever you want to input to show your symmetry. So now let's go back to the calculator. For cubed, I'm going to use this A to the B button, and it moves that cursor up. Then use the arrow to get out of the exponent. Negative 18. Let's do the same thing. Oh no, Miss Weiss. I should be inputting positive 2. So this 2 coefficient stays. It's the input of x that I'm changing. Glad I caught my mistake. Okay. 2 times 2 power cubed plus 2. Positive 18. Same number, opposite signs, so that is odd symmetry. All right, I'm going to pick another favorite number. Let's use 5 and negative 5. Positive, negative, same number. So that gives me an odd result. All right, so now we've got power functions here with this x to the 1/2. Let's do 4 and negative 4. 4 to the 1/2 power, negative 4 to the 1/2 power. Two. Undefined. That's because this power of 1/2 is the square root function. And square rooting a negative, that leaves us with an imaginary number. So 2 and undefined, that's nothing. They're not the same. All right, let's do another one. Let's do 4 again. Oops. 4 to the 4/7, negative 4 to the 4/7. Too many tabs open. Okay, clear all. .208. All right, we'll see. All right, let's do negative 4. I'm not going to write that whole number on my paper just yet. Oh, look at that. Both values are the same. There you go. Now I didn't have to write it. Both values are the same, so that means even symmetry. Okay. Describe the end behavior of the following functions. 2x squared plus 1. So I could use my knowledge of parabolas and transformations, up 1, vertical dilation of 2, and I get this parabola shape. So end behavior, we've got right and left. X goes to infinity, y goes 2. As x goes to infinity to the right, y goes up to infinity. For left end behavior, that's out here. X goes to negative infinity out to the left. Y goes to positive infinity as well. Let's say I don't remember my graph. Make a table of values. Let's input bigger and bigger numbers for the right end behavior. And let's input smaller, well, big negatives for left end behavior and see what the y's are approaching. We got this scientific calculator. Let's use it. All right. So 201. Then I'm going to do that again, but with 100 put in. 20,000. The numbers are getting very big. Sorry, that's for this one. Very big, very quickly. 2 million. So see how these numbers, these y values are getting bigger and bigger and bigger. That's showing the y's going to infinity. When I input the negatives, the same thing, we're going to get bigger and bigger numbers. Can I do this? Yes, I can. Okay, look at that. I'm going to click in these boxes and input the negatives. Now, negative 100 squared is negative times negative, which is positive. So we're getting the same outputs for my negative numbers. Which also shows that positive infinity. So now for this function, maybe I don't want to graph it. So let's look to the left. Let's look really far to the right. And input to this function x to the negative 2/3. Clear. So let's start with my left. Do negative 100. Negative 1,000. Let's go another one. And so I can see these decimals, 0.2, 0.04, 0.01. This is annoying. 0.002. They're getting really, really tiny. So as x goes to negative infinity, y is going really close to 0. We're going to approach 0, but never get there. So let's do now the positives. And I think if I click in here, can I take out? Yes, I can. Look at that. Okay. Uh-oh. And nothing's changing again on those outputs. Let me make it small. So even with positive for the right end behavior, this was left. Now for the right, x goes to infinity. Y is still approaching 0 because these are getting really, really small decimals. All right, let's try one more. Left end behavior. Right. Negative 0.6. What happens when I do a negative 100? Negative 0.4. Negative 0.3. Let's do one more for fun. Negative 0.15. So these values, even though they're negative, as our negatives are getting smaller and smaller and smaller, that's also approaching 0. Because this would be closer to negative 1, this would be closer to 0. So our left end behavior is 0. Let's do to the right. Take out all these negatives. Oops. All right, so now we've got these positive outputs, but again, they're getting really, really close to 0, but from the positive side. So we're still approaching 0. If you're not sure, you can make a little plot. All right, this is 1. We've got 0.6, 0.4, 0.3, 0.1. And then to the left, if this is negative 1, at negative 10, negative 0.5. At negative 100, negative 0.4. At negative 1,000, negative 0.3. And so you can see this it's hard to graph with the pen. This behavior, it's getting closer and closer to 0. As we go out this way, it's getting closer and closer to 0. All right, number 3. We've got this rational function. Does it have a vertical asymptote? Yes. That is whenever the denominator equals 0. That's when x equals negative 2. Does the function have a slant asymptote? So let me look at this original form. The degree of the numerator is bigger than the degree of the denominator. So yes, there is a slant asymptote. I'm going to find it. Let's do division. I'll stick with box method so that I have enough space. X squared goes back. X squared divided by x is x. Multiply it back. X times 2, 2x. Subtract. 5x divided by x is 5. So the slant asymptote is y equals x plus 5. That's that quotient. Does it have any zeros? That's x-intercepts. Yes, that is when the equation equals 0. To solve it, I'm going to multiply both sides by x plus 2. So we get 0 equals x plus 3, x plus 4. It's already factored, so I will set each factor equal to 0. X equals -3, x equals -4. These are your x-intercepts. Oop, cross that one out. End behavior. So end behavior deals with the horizontal or the slant asymptote. So for the right, x goes to infinity, y goes to a little bit. For the left, x goes to negative infinity, y goes to, this looks like negative x. All right. With a slant asymptote, I got to figure out which way the graph's going. Is it going to go up to infinity or down to infinity? So let's use this again. Clear. I'm going to put a really big number into my x's. I'm going to put in 100. Uh-oh. Oh, okay, you got to put parentheses around your numerator and denominator. Okay, so that's a big positive. So as x goes to the right, y is going to go up to infinity. Let's put in negative infinity. No, negative 100, excuse me. All right, parenthesis, negative 100 squared plus 7 times 100 plus 12, nope, divided by negative 100 plus 2. Ah, see, that's a big negative, so the left-hand behavior is going to go to negative infinity. So again, we can use this scientific calculator to help us. That's so nice. All right, is there a hole? When I look at this function, none of these factors divide to 1, so there is no hole. Next. All right, another one of these. Is there a vertical asymptote? Yes. When the denominator equals 0, that's when x equals 3. Is there a slant asymptote? Yes. The numerator exponent is bigger than the denominator. This time I'll do long division. If you like box method, you do box method. X squared divided by x is x. Multiply it back. Subtract. 1x divided by x is 1. There's my slant asymptote. Y equals x plus 1. Any zeros? Yes, there will be x-intercepts. Set the entire equation equal to 0. Multiply both sides by x minus 3. Oops. 0 equals x minus 4, x plus 2. Set each factor equal to 0. Solve, and we have 2 x-intercepts at 4 and negative 2. And behavior again. For the left, x goes to negative infinity, y goes to, for the right, x goes to infinity, y goes to. So again, I'm going to put in a very large value for x. And again, to the right, We've got a big number, so that is positive infinity. Nope, wrong spot, wrong spot. Okay, to the right, big number, positive infinity. For left, I'm going to make this a negative, and a negative, and now it's a big negative, so that's going to negative infinity. All right, does the function have any holes? Any of these factors divide to 1? No, they do not. No holes. Make a graph. Vertical asymptote, horizontal asymptote, holes, and intercepts. Okay. The first thing I notice is one of these factors divides to 1. So there's going to be a hole. When x minus 3 equals 0, because that's the factor that divides to 1, that's the x coordinate of the hole. The compressed function now will get me everything else. So my hole is going to be at the coordinates 3 comma something. I'm going to input 3 here. 3 plus 2, 3 plus 1. And when I do that, that gets me the y value of the hole. So 3, 5 over 4 is a little more than 1. Put it up here. A vertical asymptote is when the denominator equals 0. Make that a dashed line. For the horizontal asymptote, I'm going to compare my degrees. The compressed function, they're both 1. That means we divide the leading coefficients. So 1 divided by 1 gives me a horizontal asymptote of y equals 1. Make that a dashed line. All right, intercepts. Let's do x-intercepts. Use your compressed function. So the x-intercept is when the output is 0. Multiply both sides by x plus 1. Get negative 2. Y-intercept is when the inputs are 0. That gives me 2. And I paused there for a minute. I made a mistake. The vertical asymptote's at negative 1. I put it over here at positive 1. And I was thinking to myself, well, my graph can't then go through the... Okay, so anyway, let's fix that. Whoopsies, rewind. X equals negative 1 is right here, Miss Weiss. There we go. This makes more sense. Okay. When I connect my pieces, approach the asymptote, leave a gap for the hole, approach the asymptote, and there is our accurately graphed vertical asymptote now in the correct place, horizontal asymptote, removable discontinuity, and we've got the y and x intercepts. 2 more of these. Okay. Let's see if I can do this right. For number 5b in your packet, and I see a mistake here, this is going to say x plus 3. Okay, so let's start with the hole. When does this factor equal 0? Because that's the factor that divides. That's when x is negative 3. Now my compressed function, I'm going to input -3 to x. That gives me -5 over -2, which is positive 5 over 2. So there's a hole at -3. That's about 2.5. So there. The vertical asymptote is when the denominator equals 0. This time I'm going to put it in the right spot. Horizontal asymptote, we're going to compare the numerator and denominator. The degrees are the same, so we divide these leading coefficients. X-intercept is when you set the equation equal to 0. The y-intercept is when you input 0. Oh, I'm almost out of space. Okay. Multiply both sides by x plus 1. So this x-intercept is going to be at +2. The y-intercept is at -2. That's good. They're both on the same side of the asymptotes here. There's our graph. All right, one more of these. Ooh, we got to factor the numerator ourselves. What multiplies to 4 that adds to negative? Oh, multiplies to 4 that adds to 4. X plus 2, x plus 2. There's another hole. -2 comma, the compressed function, input -2. We get 0. Woo. The vertical asymptote is when the denominator equals 0. Horizontal asymptote is going to be 1 again. I already have an x-intercept. It's a hole. The y-intercept is 2 over x. Oop. -1. Mm-hmm. And over here, we're just going to approach both asymptotes. All right, last but not least, we got graphing. I got a line with a hole. Oh, this has a hole when x plus 1 equals 0. Oh, that's this one. And look at that. The remaining factor is a line. All right, these two go together. Oh, this also has a hole at -1. But the remaining pieces make a rational graph. Let me zoom out a little bit. This hole's at -4, so that must be this one. Okay, so from these pieces, part D, this one has a hole where x is -4, so that's this graph. So by process of elimination, this one goes here. None of these factors divide, so there is no hole. Make sure you can do this entire review independently and confidently, and then you are ready for the district assessment.